Well, hello, ladies and gentlemen. So this is lecture number 3 for thermodynamics. We're going to have a number of topics today. We're going to finish off the initial introduction to the course. That's the plan for today. And then we're going to move on to properties of pure substances. So topics. We're going to finish off the introductory part of the course by looking at processes. In particular, we're going to look at 3 kinds of processes. Isobaric. We'll talk about what this is in just a moment. Isochoric. C-H-O-R-I-C. Isochoric. It's not choric, it's choric, isochoric. And then we have isothermal processes. So we're going to look at these 3 processes, and then we'll do an example. And then we will move on to properties of pure substances. So properties of pure substances. In the notes, that's chapter 2. In particular, we're going to be looking at material phases. Material phases. We're going to be looking at the phase diagram. And then we're going to do an example. Okay, so that's the plan for today. We're going to finish off the introductory material and then move on to chapter 2, which is properties of pure substances. Okay, so let's change the camera here. So let's go over processes. So first of all, what is a process? What is a process? A process is the path taken by a system through a number of states. The path taken by a system through states. Okay, so let me give you an example here. Let's say we have a piston cylinder device. What is a piston cylinder device? It is a container with a movable piston, in it. And inside the container, we have some sort of gas or some kind of material, let's say. So this is a piston cylinder device containing some kind of gas. And the piston can move up and down, okay? So it's a gas trapped in a piston cylinder device. So let's say this is state 1. And I have some, temperature, T1, and volume V1 inside of this cylinder. Okay? My system, by the way, is the gas. This is my system. System is the gas. System is the gas. And then I squeeze down the gas in the piston cylinder device. So the piston is now moving downward. So here's my gas again. And this is state number 2. So I have a T2 and I have a V2. And now I'm going to squeeze down the gas even more. And this goes down to state 3. So now the piston is even further down into the cylinder, and I'm squeezing the gas down, and I have a temperature T3 and a volume V3. A little bit hard to see there. So this gas is being squeezed, and I can plot the process. The process that's going on. Temperature, volume. I can plot the process. I start off with a fairly high volume. So here's V3, here's V2, and here's V1. So volume is decreasing. When you squeeze a gas down, usually, not always, but usually, it heats up. So if you were to squeeze a gas down, it should heat up. So in theory, this should be, let's say, T3, T2, and T1. Temperature is going up. I'm sorry. T1, T1. Hold on a second. I've got this backwards. This is V1. No wonder this is screwed up. This is my initial volume, V1. It's at a maximum. V2, and then V3 is my final volume. Temperature T1, let's say it starts off cool, and then I squeeze it down, and it starts getting warmer. So I can draw the path or the process through these states. I guess let's get this looking right. So here is T1, here is T2, and here is T3. Move things around just a little bit. There we go. Okay, so the system is starting off at state 1, moving through state 2, and arriving at the final state, state 3. So this is the direction the system is going. So on a TV diagram, a temperature volume diagram, I'm showing the process as we go from state 1 to state 3 through an intermediate state, state 2. And the path, i.e. the process, is given by this line right here, okay? So process is a path taken by a system through states, okay? So the system is moving up and to the left on the TV diagram. So that's an example of a process, okay? Now there are a lot of different kinds of processes, and some of them come up over and over and over again, and it's good to give them a particular kind of name. There are many kinds of processes that come up, that crop up over and over again when you do thermodynamics problems, and so they're actually given their own names. Let's list a few of these processes. So common processes. Common processes. I'm going to list 3 today. There's actually more, but we're going to start off with 3. As time goes on and it becomes important, I will introduce additional processes. So, common processes. Number 1, isothermal. Isothermal process. What is an isothermal process? Well, iso means constant. What do you think the word thermal refers to? Well, if you thought temperature, then you're right. So isothermal refers to temperature or constant temperature. Constant temperature. So isothermal process is a constant temperature process. In terms of a diagram, The isothermal process can be viewed, let's say we have again a TV, temperature volume diagram. So we have some kind of a piston cylinder device. So here's our system. Okay, so here's our system. I don't know what it is. It could be a gas, it could be a liquid, it could be, who knows what it is. The point is, this system goes through some kind of an isothermal process. So I can plot the isothermal process. Let's say we start off at state 1 and we go to state 2, and this is an isothermal process. That represents a horizontal line. Notice temperature. T is constant. Temperature is constant for the isothermal process. So we're starting off at some initial volume, V1, and we are going to a final volume, V2, and we're doing it isothermally. Okay, constant temperature process. So that's our first common process that has its own name. What's another process? Well, another process is isobaric. Isobaric. Well, we know the word iso means the same or constant. So what might baric refer to? Well, I'll let you think about that just for a moment. Remember, there's a unit, a particular metric unit called the bar. What does a bar in metric refer to? I'll let you think about that for a moment. So number 2, we have isobaric or isobaric. Okay? And again, iso means constant. Constant. So what quantity has a unit of a bar? If you thought pressure, you would be right. So isobaric refers to pressure or constant pressure. Constant pressure process. Constant pressure process. So again, I could have a piston cylinder device of some kind. I could take a gas or something. And instead of having temperature and volume here, I could have pressure and volume. So on a PV or pressure volume plot, isobaric processes will be horizontal processes on the plot. Let's say again we have some sort of a piston cylinder device. Okay? And we have some kind of a gas or some kind of material in here. So this is our system. How could we get an isobaric process using a piston cylinder device? Well, we could stick a mass out here and stick it right on the surface. I could put a mass right here resting on the top of the piston. And so that would apply a downward force on the piston and pressurize the system. Okay? And again, I haven't mentioned this yet, but I am assuming that the piston moves up and down freely. So here's the piston. I'm assuming the piston moves up and down freely in the cylinder. In other words, frictionless. Frictionless piston. Frictionless piston. Okay? There's no friction between the piston and the cylinder. And if I stick a mass on top of the piston, that applies a weight and produces a pressure inside of the piston cylinder device. So it will be a constant pressure. Okay, it'll be a constant pressure due to the presence of the mass. So let's say I let this system expand. No, I'll let this system be compressed. So this is state 1 and state 2. Kind of running out of room here. Let's do what I can. This is state 2. I'm going to compress this system. Maybe it's a gas, who knows. So again, here's my system. Could be a gas system. And again, I got my mass here. That's applying the constant pressure. So I'm going to squeeze down the system. And so state 1 will start out here with volume V1. So originally I have a volume V1. And I have some kind of pressure, obviously. And then I am going to isobarically compress the system. If it's a gas, then I'm compressing the gas, okay? So this is what the process looks on a PV diagram. So I'm compressing the system. I end up at state 2, which has a volume V2. And of course, the pressure is the same. So this is state 2, and this is my pressure, okay? Pressure is constant. Pressure is constant, okay? So the system is moving from right to left. There's the process, state 1 to state 2 along an isobaric path, okay? So this is a very common process. Isobaric processes are very common. They often come up in piston cylinder type problems, okay? Isothermal, not so much, but isobaric processes often come up for piston cylinder devices, okay? And you'll be doing some examples on that later. Let's do another one. Got one more process we want to look at. Very common, and that's isochoric. Isochoric, how do you spell that? C-H-O-R-I-C, isochoric. So number 2, isochoric process. Again, iso means constant or the same. Choric is actually a strange way to describe, or word to describe volume. So isochoric process means constant volume. Constant volume, okay? Constant volume process. Now, what might an example of a constant process, constant volume process? Let's say we have a container, a rigid container. So rigid container, and it contains some kind of gas. So this is our system, some kind of gas or something, okay? State 1. State 1, I have, I don't know, some temperature T1, some pressure P1, and of course I have a volume V1. And now I'm going to add some heat. I'm going to add some heat to this rigid, this gas contained in a rigid container. Look at what I'm drawing here. We're going to state 2, and we go to state 2 by adding heat. Look at the arrow. The arrow indicates I'm adding heat. So I'm going to put Q here. I'm adding heat, and I end up with state 2. So here's my rigid container, and now I have a temperature T2, a pressure P2, and of course I have a volume V2, which is equal to V1. It's a rigid container. Rigid container, no volume change, isochoric process. Rigid container, okay? So I'm adding some heat as I go from state 1 to state 2. I'm going to put a little subscript on here as well. Heat added from state 1 to state 2. 1 arrow 2, okay? So I'm adding heat, and the system is moving from state 1 to state 2 isochorically as I add heat. What do you think is going to happen to temperature or pressure? What's going to happen to temperature or pressure as I add heat to this gas in a rigid container? Well, it should heat up, so temperature will go up, and also if the container is rigid, the pressure should go up too. The gas wants to expand, but it's got nowhere to go. It's a rigid container, so pressure should go up and temperature should go up. So I should have, here's a TV diagram, temperature, volume. And so the process looks like a vertical line from state 1 to state 2, where I have a temperature T1 and temperature goes up to T2. So temperature is going up and the process is isochoric. Volume stays constant. So this is V1 is equal to V2. Isochoric. Isochoric. Pressure is going up too. So let me put up the PV diagram. Pressure volume diagram. Volume, so here is state 1, and I have a pressure P1, and I add heat, and pressure goes up to P2, and I end up at state 2, and of course volume is constant, so V1 is equal to V2. So that's what the processes look like. An isochoric process looks like on a TV and a PV diagram. Constant volume, constant volume. Now, before we finish here, I do have a little question for you. Gonna see if you understand what's going on here. Let's say I gave you the following process. Let's say I gave you the following process. I'm just going to throw this out here and say something about it. Let's say I have a pressure volume here. And let's say I have the following process. Here's state 1. And this is what my process looks like. State 2. Note that P1 is equal to P2. Volume, of course, is increased. So this is V1 and V2. So obviously volume's increased over this process. Note, P1 is equal to P2. Is this an isobaric process? Isobaric means constant pressure. The answer is no. This is not an isobaric process. Pressure is changing along the path. So it's not an isobaric process. Just because your starting and final value for pressure is the same does not imply automatically that it's an isobaric process. Okay? Here's another one. Here's temperature and volume. State 1. Around in a circle. Notice, I guess I can, so there's our volume there at the end. So I guess this is state 1 and it's state 2. We go along a path and we end up back where we started. So V1 is equal to V2 and T1 is equal to T2. So the initial and the final state are the same. We just go around in a circle on the TV plot. Is this an isothermal process? T1 is equal to T2? The answer is no, it's not a constant temperature process, so it's not isothermal. Likewise, is it an isochoric process? V1 is equal to V2? The answer is no, it is not a constant pressure process. A constant volume process. Constant volume would be a vertical line on the TV plot, and constant temperature, isothermal, would be a horizontal line on the TV plot. Okay, so none of these examples are iso anything. Okay, none of them are iso anything. Let's do an example here. Let's do an example involving processes. Okay, involving processes. Let's do an example involving processes. Example. By the way, before we get going here on the example, let me show you what is recommended on the homework and doing problems in thermal. I had that handout posted on guides to doing homework. Let me show you how that's done. Let me go to screen share here. Now what I have here, this is the notes. The handout is more or less the same thing as the notes. If you go to the very end of the notes, nearly the end of the notes, you'll see a section on this Appendix A, coursework format with example. So let's go over how the coursework or the homework is supposed to be done. So you should have your green engineering paper, put your date, the course, your name, and the page number, page 1 of 2 or 1 of 5 or whatever it is. I suppose you can do it, the max pages could be for the entire homework or it could be for each individual problem. It's up to you. And then you have the problem statement. So you need to write down word for word what the problem statement is. Okay, so we know what the problem is. And then you put a nice black, thick black line right here. Okay, nice black line. And then right below it, you have a section called given. And in this section, you translate the problem into mathematics. What are you given? Okay? And then you have a section called find. What is it you were supposed to find? Give the symbols, give the variables for what it is you were supposed to find, the mathematical expression for what you were supposed to find, okay? Then if there is any schematics that are involved with the problem, any pictures that are used or given, then you should have the schematics. And then you should have a section called assumptions. If you're looking up any data, if you have a system that's made out of a particular material and you need to get properties, we'll talk a little bit about this later, but if you need to get properties out of tables to do the problem, then you need to write down where you got the data from, where you got the properties from, okay? Any sources for the problem need to be listed in the assumptions. Also, any assumptions on the behavior of the system. We'll talk a little bit more about assumptions as we go along, but there is this assumption section. And then finally, we have the analysis section where you proceed mathematically through the problem, calculating, or eventually arriving at your solutions and your answers. When you're all done and you have numerical results, you box them up at the very end of your homework. That way, your boss, yourself, the grader, me, can look down at the very bottom of your work and see your answers, okay? Of course, we'll check how you got the answers, but the answers should be listed at the very bottom. Here's an example. Here's an example. You don't have to worry about this. This is a little bit complicated. We have a process involving air moving through a couple of devices. I see the word isobaric here. Don't worry about this reversible and all this other stuff. Here is a diagram. It's a TS diagram. S is actually entropy. We're not going to get to entropy for about 4 or 5 weeks, so don't worry about that. But you got a diagram. You've got a diagram indicating the process. You've got your givens, initial states, intermediate states. Any givens are listed here in mathematical form. The problem statement is given up here. So you should write this down, the problem statement, distill it into in mathematical form using the givens, indicate what variables or what quantities you're supposed to find. Apparently, we're supposed to find some temperature, T1 and T2 in this problem. Assumptions, you've got a list of assumptions, including sources for properties. So some properties are evaluated here. You see Moran and Shapiro listed, and a table A20 is listed here. So apparently we got some data out of a table A20, and that's indicated in the assumptions, all right? And then you've got the analysis, and you've got a bunch of equations. It looks like the first law, the energy balance, and you do a bunch of stuff and calculate your results, okay? So that is how I expect you to do the problems in your homework. So let's go over an example here. So let's go over an example involving processes. I'm not going to give you a problem statement. Let's assume there's a problem statement. I'm going to go immediately to the given, but I'm going to write problem statement. If you got a problem statement for the homework, you should write it down in the problem statement section. So I'll write some quotes in here, and I'll close it up. Now, what I'm giving you, I'm going to put a schematic up. I'm going to go right to the schematic. Right to the schematic here. I have a piston cylinder device going through a number of different processes. Okay, and this thing contains a system like some kind of gas. Okay, some kind of gas. So this is state one. So initially we have a volume V1, a pressure P1, and a temperature T1. And then I go to state two. The volume, I'm going to give you the process in just a minute. It looks like the volume remains constant. So this is state two. And we have a pressure P2, a volume V2, and a temperature T2. And then, running out of room here, it looks like the gas expands. So we're going to let the gas expand. Here's our gas. And this is state three. And I have a pressure P3, a volume V3, and a temperature T3. Let me give you the processes here. So we have a given section. Given the initial volume, V1 for our gas. So we have a gas in a piston cylinder device. Gas in piston cylinder device, okay? Gas and piston cylinder device. Your initial volume for the gas, V1, is equal to 0.4 cubic meters, okay? The final volume, V3, is equal to 2 times V1, okay? So it doubles in volume, at least from the initial to the final state. The pressure, P1, is equal to, the initial pressure at state 1 is equal to 150 kPa. And pressure P3, that's the final pressure, is 350 kPa. Okay? Now, what are the processes? Oh, sorry. Let me stop sharing here. Sorry about that. Getting ahead of myself. Okay, so we have a piston cylinder device. It goes through 3 states. State 1 to state 2, and then to state 3. It's a gas or something in a piston cylinder device. Sorry about that. We have our problem statement. You'd write that out. And then I got my givens. Gas in a piston cylinder device. My initial volume is 0.4 cubic meters. My final volume is twice the original volume. My initial pressure is 150 kPa, and my final pressure is 350 kPa. So that's what's going on in this particular problem. Okay, let's, what are the processes? Process 1 to 2 is isochoric. Isochoric process 1 to 2. You can kind of see that the piston isn't moving. And then we have process 2 to 3. That is going to be isobaric. Okay? Isobaric. Process 1 to 2 is isochoric. Process 2 to 3 is isobaric. What are we supposed to do? Find. Let's draw the process or find the process on a pressure volume diagram. PV diagram of process. We're going to draw pressure as a function of volume for process 1 to 2 to 3, okay? Process 1 to 2 to 3. Okay, so I'll tell you what, why don't I stick on the same board and I'll do the process. Oh, by the way, what are the assumptions in this particular exercise? Assumptions, I'll write it right here. I wish the resolution was good for both these boards together, but one at a time is pretty much maximum. In the assumption section on the homework, just put none. In this particular problem, just put none on the assumptions. We're not making any assumptions when we're doing this particular problem. Okay? So analysis. It just involves a plot. Analysis. Well, pressure, volume. First of all, let's put state 1. We know everything about state 1. We know the pressure and the volume. So let me put pressure and volume on the plot, okay, for state 1. So this is P1, which is 150 kPa. This is going to be in kPa. Okay? And volume is going to be in cubic meters. Okay, so we start off with 150 and 0.4 cubic meters. So this is state number 1. That's state number 1 right there. Okay, that's state number 1. All right. Now we're told process 1 to 2 is isochoric. Isochoric means constant volume. So I'm going to write right over here, V2 is equal to V1. Why? Because it's isochoric process. V1 is equal to V2, so it's an isochoric process. Okay, so V1 to V2 is an isochoric process. So that means volume remains constant, and we're moving up and down this line here, okay? Now the question is, what is P2? So this is V1. V1, which is equal to V2, which is 0.4 cubic meters. The question is, what's P2? How far do I go up vertically? How far do I go up vertically or down? I suppose pressure could fall. Where do I go vertically on this PV diagram? Well, the answer is, note that process 2 to 3 is isobaric. So P2 is also equal to P3 because it's isobaric process. Okay? So let's put P3 in. P3 is 350 kPa. So P3 is actually equal to P2, which is equal to 350 kPa. So here's 350. So state 2 must be right here at pressure P2, which is equal to P3, which is equal to P3, okay? So 1 to 2, that's process 1 to 2. We know P2, we know the volume, we know the initial pressure. It's isochoric, so it has to move on this vertical line. So process 1 to 2 is a vertical line from P1 up to P2, which is equal to P3. Process 2 to 3, let's draw that one. That one has to be along a horizontal line in PV space, has to be along a horizontal line. So the question is, what direction do we go? Is volume going to decrease or increase? Well, note, we're told that V3 is equal to 2 times V1. So V3 is 2 times V1, which is 2 times 0.4 meters cubed, or if you like, sorry, I'm running out of space. I want to do this all on one board. 2 times 0.4 or 0.8 cubic meters, okay? V3 is 0.8 cubic meters because volume is doubling from state 2 to state 3. So here is V3, which is 0.8 cubic meters, and the process is isobaric, so it's going to be a horizontal line. And this is state 3, okay? So that is the process. 1 to 2 to 3. That is the process. 1 to 2 to 3. The overall process, all right? So that's how you're supposed to do a problem. Of course, don't squish things up quite as much as I've done it here because I'm trying to get everything on one board, okay? Trying to get everything on the same board. Space it out a little bit better in your homework assignment, okay? Okay, so I think that's it on chapter 1, or introduction to thermodynamics. Oh, by the way, I have posted, let me see if I can find it here. I have posted, let's see, where is it? Let me see if I can find it. Posted on Canvas. Yes. Posted on Canvas. This is not it. Where is it? There it is. I posted on Canvas a document called Concepts and Definitions, Fundamental Concepts, Terminology, and Definitions. It gives written definitions for system, properties, state, process. Don't worry too much about some of this other stuff first. This thing called surroundings, isolated system. Don't worry too much about continuum. You can read these if you want. You can read these if you want. I'm not going to go through too much on this. But I have provided you with a document on Canvas that goes over and repeats some of what we've done for the concepts here, okay? Okay, I'm going to break this before we go on to chapter 2 here. Going to break the lecture. All right, ladies and gentlemen, let's move on to chapter 2 in the notes, which is properties of pure substances. So let's look at properties of pure substances. Properties of pure substances. This is where this is necessary material so that we know how to describe the properties of a system, and we can start applying the energy equation and eventually the entropy equation. Before we can apply balances, we need to know what the properties of the system are, or how to find the properties of a system. Temperature, pressure, specific volume, whatever. Okay? So that's what this chapter is about. First of all, let's go over the different phases associated with pure substances. So let's look at phases. Phases. Well, the most basic phase that I think we're all familiar with is solids. So we have solid phase, solids. So in terms of chemistry here, solids, so these are atoms. Solid phases are characterized with very strong atomic and molecular bonds, very strong molecular bonds between atoms. So we have strong, or if you like, rigid molecular bonds. Molecular, strong, rigid, molecular bonds. Strong or rigid molecular bonds, all right? Now, if you place a solid in a container, so here's a container. If you place a solid material in a container, it does not fill up the container. So you put a solid in here, so here's a solid block of something. It doesn't fill up the container, it conforms to a particular space, okay? So a solid in a container just sits there, okay? Now, what about a liquid? Liquid phase. What about liquid phase? Well, so here we have the atoms and the molecule, and these bonds are kind of weak. I'm just trying to sort of indicate that these can move around. So weaker bonds. Weaker bonds. So that's for a liquid. So the atomic bonds and the molecules, the bonds between the atoms, the molecular bonds are weaker. And the attraction between molecules are weaker as well. So if we have a container, so here's a container right here. If you put a liquid in, a liquid material, it conforms to the container and it produces a free surface. So here we have a liquid. So it conforms to the container, but it also forms a free surface. Free surface. That's a boundary or a barrier between the liquid and everything else, okay? So it forms a free surface, forms a free surface. That's what a liquid, that's how a liquid behaves. It conforms to the boundary of a container, but forms a free surface. Now, what about gas? What about a gas? Well, similar to a liquid, it conforms to the inside of the container, except it does not form a free surface. So we got vapor, or if you like, a gas, okay? Vapor or gas. And we have the molecules or the atoms here, and the bonds or attraction between them is very weak. So we have weak bonds between the molecules and the atoms, okay? Weak bonds. I guess I should say weak bonds between the molecules. That's probably the best way to say it. And if we put a gas in a container, so the gas fills the container, and doesn't form a free surface. It simply fills the container, okay? conforms to the container. No free surface like we had for a liquid. The liquid forms a free surface as a barrier between itself and everything else, okay? So, vapor, liquid, solid. 3 different phases, and all materials exhibit these particular phases depending on their temperature and pressure, okay? Depending on temperature and pressure. Okay, let's get started here. Let's get in a little bit deeper here. Let me switch cameras. Let's look at a process involving water, or H2O. Let's look at a process involving water, or H2O, in a piston cylinder device. So let's say we have a piston cylinder device. Here it is right here. And here's the piston. I'm not going to draw it circular. I'm just going to put the piston in here. There's the edge of the piston. Some more chalk. So we start off here with water. There's a pressure applied, or there's a mass on top of this piston. Actually, no, there's no mass on top of this piston. Let's just leave it off. So the pressure inside of this piston cylinder device is water trapped inside this piston cylinder device. Let's be easy on ourselves, and let's say it's 1 atmosphere. 1 atmosphere. So pressure, P, equals 1 atm. 1 atmosphere, atm. Okay? So we're going to look at the isobaric heating process for air. Isobaric, not air, water. Isobaric heating of H2O. Isobaric heating of H2O. That is what we're going to be looking at for this process that we're going to be looking at over the next few minutes. Let's say the original temperature, so this is P1. Let's say the temperature T1. Well, water boils at 100 degrees C. Let's say the initial temperature is room temperature. Let's say 25 degrees C. So let's say the original temperature is 25 degrees C for this water. Now over here, how do I want to do this? 2 boards, hard to do, looking 1 board at a time. So this is state 1. I'm going to put up a temperature specific volume. So this thing originally has some volume V1 and a certain amount of mass inside. So remember, specific volume is mass, specific volume is volume divided by the mass of the system. So I have an initial volume, state 1 for my H2O, and there's a certain amount of H2O mass in my piston cylinder device. Okay? So specific volume at state 1 is equal to volume at state 1 divided by mass. Okay? Now, let me put state 1 up here on my temperature specific volume plot. Units for specific volume in metric is cubic meters per kilogram. And let's say temperature is in centigrade. Degrees C, okay? Temperature in degrees C. State 1, I start off at 25 degrees C. And I have some specific volume. I don't know what it is. I'm just going to put V1 right there, lowercase v1. So that's state 1. That's state 1. Now I'm going to add some heat, and I'm going to add it isobarically. I'm going to let this piston move up or down, maintaining the pressure constant inside of the piston cylinder device. So I'm going to add some heat. Okay? We're going to add heat Q1 to 2. I'm going to add some heat. And I'm going to add heat until the temperature goes up to, let's say, 90 degrees C. So now as I heat the water, it should expand a little bit. So to keep the pressure the same, the water will have to expand a little bit. And so the piston will move upwards just a little bit. Piston will go upwards just a little bit. This is isobaric expansion. So the piston moved up just a little bit, and I have a new temperature, T2 equals 90 degrees C. Okay? And I also have a new specific volume, V2 greater than V1. Okay? Pressure is the same, so it's isobaric process. Okay? Let's see, let me put up state 2. So let's say state 2. So here's state 2. I'm now at 90 degrees C. Okay, 90 degrees C. Tell you what, I am going to move this a little bit. Volume doesn't change much at all. So I'm going to put V2 right there. Volume doesn't change much at all, but temperature has changed quite a bit. Okay? So that's state 1, and that is state 2, okay? Adding heat, expands, temperature goes up. We're still water, okay? Now let me add a bit more heat. Let's move over here, add a bit more heat. Oops. Here. Sorry about that. I guess I should put this in my pocket. Okay, so let's add a little bit more heat. And we're going to add just enough heat so that the liquid water just begins to boil. We're going to go right up to the boiling temperature. So I'm going to add a little bit more heat, Q2 to 3, and we're going to end up at state 3. The piston will have gone up just a little bit more, and we're now at the boiling temperature. So T is equal to, and by the way, I don't think I said, but I think it was implied, what is the pressure? What's the pressure in which I'm doing this process? I'm going to make it 1 atmosphere. Isobaric heating of H2O, pressure 1 atm. So just a little reminder, I'll write it down here too. Pressure 1 atmosphere. We're heating water at room pressure, 1 atmosphere, okay? So we're going to add heat until we just get to the boiling point. Boiling point. Or a more scientific way to say that is we will have saturated liquid. Saturated liquid. That means liquid just ready to boil. We started off with liquid water at 25 degrees C. We heated it up to 90. It's still liquid. And then we're going to heat it up until it's just ready to start boiling. What temperature does water boil at 1 atmosphere? In metric, it's 100 degrees C. So T3, I'm going to erase this boiling point here. If you want to put it down in parentheses here, I guess I'll put it down here. Boiling point. So T3 is called the saturation pressure. It's the boiling pressure. T3 equals T boil equals T saturation. 100 degrees C, okay? So we're going to heat it up to 100 degrees C by adding just a little bit more heat. It's liquid, but it's saturated liquid. Saturated liquid, just ready to boil. Just ready to boil. So let's put that additional state number 3. So this was 90 degrees C, and now I'm going to go up to 100 degrees C. Okay, so that's state 3. So that's state 3. 1 to 2 to 3. Liquid is just ready to boil. Okay, let's add a bit more heat. Remember, we're doing this isobarically at 1 atmosphere. So now we're going to add Q3 to 4. We're going to add some heat. What I'm going to do is I'm going to add some heat until some of the liquid starts to boil away. The vapor that's produced is trapped inside the piston cylinder device. It can't go anywhere, but the H2O is going to expand because now we have gas and liquid together. So the piston is going to go up. The piston is going to go up. And I'm going to have a mixture of saturated liquid and vapor. So I'm going to add heat until I have a mixture of saturated liquid and saturated vapor. Okay? And if I measure the volume of the whole thing, so I have a certain volume, V4. I have a certain mass, so I have a specific volume, V4. And I'm going to put that up on my diagram in just a moment, okay? Now, question, when you're boiling water on the stove, which is isobaric boiling, does the temperature of the water go up as you boil the water and you add more and more heat? You stick a thermometer in that boiling water, does the temperature keep going up as you boil the water away? And the answer is no. Temperature remains constant. Temperature remains at 100 degrees C during the boiling or the vaporization process. So the temperature in here, T4, is still equal to Tsat for 100 degrees C. Temperature is still equal to the saturation temperature, 100 degrees C. Now, the volume has gone up. The volume has gone up clearly because we boiled some of the liquid away. So note, specific volume at state 4 is greater than the specific volume at state 3 because it's expanded and we boiled away some of the liquid. So let's put this state 4, on the temperature volume diagram. Let's see here, state 4 temperature is the same, it's still 100 degrees, but specific volume has increased. So here's specific volume at state 4. By the way, I didn't put specific volume at state 3, you can barely see it. Okay, but temperature remains the same. So during a boiling process, provided pressure is constant, temperature is constant. So state 4 has the same temperature as state 3, and its specific volume has gone up because the liquid is boiled away and volume has increased. So specific volume has increased as well. Let's add some more heat. Let's get to state 5. Let's add just enough heat so that all the liquid is boiled away. Just enough heat to boil away the remaining saturated liquid. Going to have to make my piston cylinder device deeper. as I boil away the rest of the liquid, the volume is going to increase even more. So make it a little bit deeper. Here's the top of my piston. Here's my piston right here. All the liquid has boiled away, so this will be state 5. So I'm going to add heat to boil away all the remaining saturated liquid, and then I simply have saturated vapor. No liquid. No liquid. So I added just enough heat and no more to boil away the last drop of saturated liquid in my container. So that means temperature is the same. T5 is equal to T sat. So that was T4, T3, and that was 100 degrees centigrade. I'm just going to get rid of that T4. So T5 is still equal to T sat, which is still 100 degrees C. T sat is a fancy term, and T saturation, or the saturation temperature, is a fancy name for the boiling temperature. T saturation means boiling temperature, okay? And note that the piston has gone up, so the specific volume at state 5 is greater than the specific volume at state 4. So it's expanded more because we boiled away more of the liquid. We boiled away all of the liquid. Let's put this on our temperature volume, specific volume. Okay, so temperature is the same. It's an isothermal as well as isobaric boiling or vaporization process. Here's the specific volume at state 5. And we're still at T sat, 100 degrees C. T sat at 1 atmosphere is 100 degrees C. And what I mean by that is boiling temperature. Boiling temperature, 1 atmosphere, 100 degrees C by definition, okay? Okay, let's add just a little more heat. So I want to point out here, that we're going from state 3 to 4 to 5. We're starting off with a saturated liquid. The liquid is just ready to start boiling. You add a little bit of heat and a drop of it will immediately convert to a vapor. So we start off with a saturated liquid. It's just ready to boil. It's at 100 degrees. Then we add heat. Some of the liquid boils away to produce a saturated vapor. So we have a mixture of saturated vapor and liquid at state 4. And then state 5, we're adding a little bit more heat to finally boil away the remaining liquid. And we get a saturated vapor. You can think of a saturated vapor as vapor which is just ready to condense into a liquid. This vapor is at 100 degrees C, which is the boiling temperature or the saturation temperature at 1 atmosphere. So if I were to cool this, try to extract out just a little bit of heat from this vapor, immediately droplets would start condensing and I would get a liquid phase in the container. So saturated vapor means it's just ready to condense. Saturated liquid means it's just ready to boil. Let's add a little bit more heat and we'll be done. Q5 to 6. Gonna add just a little bit more heat. Okay, we started off with the saturated vapor, and then we add more heat, it's gonna get hotter. It's gonna get hotter and it's gonna expand, provided we keep pressure at 1 atmosphere. So I need to make my piston soda device really deep. And that piston's gonna move upwards a little bit more. Okay? So volumes increase. So V6, state 6. V6 is greater than specific volume at state 5. We've added more heat, And so now temperature at state 6 is going to be greater than temperature at state 5, which was Tsat at 1 atmosphere. And of course, volume at state 6 is greater than volume at state 5. Hence, specific volume at state 6 is greater than specific volume at state 5. Specific volume is volume divided by mass. The mass isn't going anywhere. There's still the same amount of H2O in there. But now, instead of having a saturated vapor, it's now hotter. It's hotter than the saturation temperature, so it's superheated vapor. Superheated vapor. Why? Because temperature is greater than Tsat. Temperature is greater than Tsat, or the boiling temperature, so it is superheated. Specific volume's gone up, temperature's gone up. Let's put this on our our temperature specific volume diagram. So now we're at some new temperature. I guess I need to make a temperature up here. T6, I don't know, 150 degrees C. I'm just making something up. So let's make T6 150 degrees C, okay? And specific volume has now gone up. So specific volume at state 6. Okay? So there is the path from state 5 to state 6. Okay? Okay, let us redraw this diagram without some of the numbers. Okay, let's just redraw this TV diagram. Temperature, specific volume. Forget the numbers, forget the units, okay? Make sure I'm on the right screen. Good. Okay, so the process looks something like this. 1 to 2 to 3. And in this region right here, in this region right up to state 3, we were a liquid. Okay, we were a liquid, but we were a liquid below the boiling temperature. Remember, right at state 3, we were at 100 degrees. Below state 3, state 2 or state 1, we were at a lower temperature than the boiling temperature. So at state 1 and 2, we were super cooled liquid. Supercooled liquid, state 1 to 2, all the way up to state 3. At state 3, we were a saturated liquid, just ready to boil. The temperature here at state 3 was Tsat. Tsat at state 3, okay? From state 3 to 4 to 5, in between here, we were a mixture from 3 to 4 to 5, in between here, we were a mixture of saturated vapor and saturated liquid. So in this part of the diagram, we were a saturated vapor plus liquid mixture. Saturated vapor liquid mixture. There's state 5. Here we're a saturated liquid. Boiling occurs, and I have a mixture of vapor and liquid. And then I get to state 5, and I have saturated vapor. State 5 is saturated vapor. State 5, saturated vapor, 100 degrees, okay? Then I add a bit more heat and temperature goes up, and I get to state 6. When my temperature exceeds the saturation temperature, I'm out here. This is what's called a superheated vapor. Superheated vapor, okay? So there's several different states or phases here. We've got a supercooled liquid where the temperature is below the saturation temperature. So we got temperature below Tsat for some pressure. If temperature is below Tsat for some pressure, we are some kind of a super cooled liquid. If temperature is greater than Tsat, at some pressure, evaluated at some pressure. See this vertical line at a pressure, evaluated at a pressure. Then we have superheated vapor. Temperature above Tsat, we are in the superheated vapor part of the isobar, okay? If you're at a temperature equal to the saturation temperature, T equals Tsat, at some pressure, well, that implies you're saturated something. You're saturated something. Could be a mixture, could be a liquid, could be a vapor, or again, a mixture, okay? Let me put in some specific volumes of interest here. It's a bit difficult to see here, but let's draw a dashed line at state 3. V3. Let's put V3 in here and specific volume at state 5. So at state 3, we have a saturated liquid, and at state 5, we have a saturated vapor. So we can call these specific volumes V3. V3 is equal to the specific volume of the saturated liquid. So I'll put SAT LIQ, sat liquid at some pressure. V3 is the saturated liquid, specific volume at some pressure. At state 5, we're saturated vapor. So this is V of the saturated vapor at some pressure, P. Okay? Let me show you what some of these are. Let's go back to the notes. So at the very end of the text, we have Appendix B, which is property tables. You have some molecular weights. Don't worry about this T-crit and P-crit just yet. You got some chemical formula, molecular weight for various things. So here we have water down here, H2O. Molecular weight, kilograms per kilomole, is 18.02. Got this from chemistry. Look at table B2. B2 is saturation temperature table. I've got temperatures and I've got pressures. You give me a pressure in bar, and I can give you the saturation temperature T. You give me a pressure, I give you the boiling temperature. Let's see here. We also have saturation pressure tables. You give me the pressure, I give you the temperature. One atmosphere is basically 1.01 bar. So here, let's put some numbers in here. Let me get back here. Let's put some numbers in here. So let's say we are at 1 atmosphere. Let's use these tables to look up the boiling temperature or saturation temperature of water. So pressure equals 1 atmosphere. It's about 1.01 10 to the 5th pascals, okay? Or if you like, 1.01 bar. A bar equals 1. 1 bar is equal 10 to the 5th pascals. Okay, that's what a bar is from metric. Okay, so let's find out the temperature T boil, the boiling temperature at 1 atm. If you like, T stat. I guess I use the superscript here. I forgot whether I use superscript or subscript. I guess it's the, well, so T sat at pressure equals 1 atmosphere. Or if you like, 1.01 bar. It's actually 1.014. So let's have a look here at our saturation tables. So this is from the text. Okay, let's see if we can find a pressure equal to 1 atmosphere. This is in bar. 1.014, that's actually 1 atmosphere right there. Move over to the left. T sat, or the boiling temperature, at 1 bar. T sat at 1 bar is 100 degrees C. So 100 degrees C. It's actually 1.014 bar, if you want to be precise. So I'm going to put a 4 here. 1.014 bar. Okay. I'll put the 4 here too. All right. And we got this from table B2, saturation tables. Saturation tables. Let's use these tables just a little bit more. Let's find out the specific volume. Let's find out the specific volume for, let's find the specific volume for the saturated liquid and the saturated vapor. Let's see how this works. Okay? Okay, so we have some quantities here. There's specific volume. Saturated liquid specific volume times 10 to the 3. It has units of cubic meters per kilogram. Saturated vapor specific volume, cubic meters per kilogram. Notice it's 10 to the 3 here. That means whatever numbers are in this column, the saturated liquid specific volume times 10 to the 3 is equal to this number, okay? So we are at 100 degrees C, 1.014 bar, and the specific volume of the saturated liquid is that third column. Here that looks better. So there's the relevant row. Specific volume for the saturated liquid is 1.0435 times 10 to the minus 3. Specific volume of the saturated liquid evaluated at temperature of 100 degrees C. By the way, that's also equal to a pressure of 1 atm, is equal to 1.0435, 10 to the minus 3. 1.0435, 10 to the minus 3, and that has units of cubic meters per kilogram, okay? The specific volume for the saturated vapor at 100 degrees and 1 atmosphere, that is 1.673. T equals 100 degrees C, pressure equals 1 atmosphere, 1.063, let me check and make sure that's right again, 1.0673 cubic meters per kilogram, okay? So that's specific volume for the saturated liquid and vapor, okay? 1.0435 times 10 to the minus 3, and 1.067, no 10 to the minus 3, no 10 to the minus 3, cubic meters per kilogram, cubic meters per kilogram. So that's how you use these tables. Quite nifty, quite nifty, quite nifty. We'll do an example involving these tables here soon. Let's finish this off here, and then we'll do an example next time involving this stuff. Let's just finish off the material. So you can see on the right board, for a particular pressure, I heated up water. Started off as a saturated liquid. I heated it up until it started to boil. I vaporized it, and I continued to heat it up. That was for one pressure. So this guy here, this is for a pressure equals 1 atmosphere. 1 atmosphere. This is an isobar. Isobar means same pressure. That is an isobar, 1 atmosphere pressure. What if I were to conduct this experiment for many different pressures? Many different pressures. Let me reduce the pressure, rerun the experiment. Let me increase the pressure, rerun the experiment. So, temperature, specific volume. Here's our original isobar. Oops. Okay. So this is P equals 1 atmosphere. That's 1 isobar. Okay. And of course, the temperature, saturation temperature is 100 degrees C. Let me reduce the pressure. Let's see here. What happens to the boiling temperature when we reduce pressure? If you try to boil water in Denver, which is a mile high, what happens? Well, the water boils at a lower temperature. Water boils at a lower temperature. So if I rerun the experiment at a lower pressure, so let's say this is P1. If I rerun it at a lower pressure, I will get the following. So looks something like this. And then it starts to boil at a lower temperature. Okay? So this is P2, which is less than P1. Okay? Lower pressure, lower pressure. And now let's increase the pressure. Let's increase the pressure. So this is P3, which is greater than P1. You increase the pressure, boiling or saturation temperature goes up. Let me give you some numbers here. Let's see here. Go back and share this. Let's see here. Let's say, let's go to the pressure table. I don't know what the pressure is in Denver. If the pressure is 8/10 of an atmosphere, more or less, it's down to 93 degrees. I'm not quite sure if it's that low, but let's say P2 is 0.8 bar. So the boiling temperature would be 93 degrees C. So let's say P2, 0.8 bar. If that's true, then it boils at 90.8 bar. It would boil at 93 degrees, 93.5 degrees. And if I cranked up the pressure, let's say we go to 2 atmospheres, which is approximately 2 bar. Let's say my pressure P3 is 2 atmospheres. The temperature, boiling temperature, would be 120 degrees. So P3 is 2 bar, and the temperature would be, I'm going to switch the screen back on in just a second, 120 degrees C. So we've done looking at boiling pressures here. Let me get back to the screen. So all I did is I added in the 93.5 degrees C, which corresponds to the 0.8 isobar, and the 120 degrees C, which corresponds to the 2 bar isobar as well. Okay? Now I got all these isobars. I can put in another one. Here's another one. This is the last isobar I'm going to put in. That thing does not have a flat mixture region. See, in the flat region where the boiling is isothermal, you've got a mixture of liquid and vapor. This one doesn't have a flat region. That last isobar where the boiling actually disappears, this gap between the saturated liquid and the saturated vapor specific volume, that last isobar, this pressure is called P crit, P critical, critical pressure. That last isobar has a pressure P critical, okay? Now, let me connect all the points for saturated liquid. I got saturated liquid right here, right here, right here, and right where it disappears. So let me connect all these points, all the points that are saturated liquid, okay? And let me connect all the points that are saturated vapor. Okay? I get a dome. Saturated liquid, saturated vapor. Inside the dome is a mixture. Let's write out the details for this saturation dome. Saturation dome. Saturation dome. What is the saturation dome? Let me draw that dome. There it is right there. Here's temperature. Here's specific volume. If I want to put an isobar in, let me put in an isobar. Here's an isobar. P equals constant. So this is an isobar. Okay? Up here at the top, where this last isobar at the critical pressure went through, is called the critical point. Critical point. There's a temperature here. T crit, critical temperature. And there's an isobar that goes through there. So there's a pressure associated with that. On the left-hand side of the dome, on the surface, is saturated liquid. Sat liquid. Sat liquid. On the right-hand side of the surface of the dome, we have saturated vapor. Sat vapor. In the middle, we have a mixture of the two. Inside, we have saturated liquid plus saturated vapor inside. The temperature here at the horizontal part inside the dome for the isobar, this is Tsat evaluated for the pressure P, the boiling temperature. Tsat at P. Over here, in this region, to the left of the surface of the dome, we have supercooled liquid. Supercooled liquid. And over here, superheated vapor. All right? Supercooled liquid, saturated liquid, saturated mixture of liquid and vapor, saturated vapor, superheated vapor, critical point, okay? Critical point. You want to know what the critical temperature and pressure are for a particular substance? How do you find this temperature and the isobar that goes through that point? How do you find the temperature and pressure at the critical point? Well, we use table B1. So T critical and P critical. Table B1 out of the notes. Look in Moran and Shapiro, you'll see a similar table is probably the first table as well. Let's see here. B1. B1, substance, chemical formula, molecular weight, T critical, P critical. For water, the critical temperature is 647 degrees C. No, I'm sorry, that's Kelvin. Absolute. 647 degrees Kelvin, so that's about about 400 degrees, around 400 degrees. Subtract 273 from that. It's actually more like 350. About 350 degrees centigrade. The critical pressure in bar, 220 bar. Basically, 1 atmosphere is a bar, so the critical pressure is 220 atmospheres approximate. If you want to know what the critical point represents physically, note on this side of the dome and this side of the dome up to the critical point, there are distinctions between liquid and vapor. You got supercooled liquid here, you got superheated vapor, you got saturated liquid, you got saturated vapor, and a mixture in between. When you get to the saturation, when you get to the critical point, the distinction between liquid and vapor goes away, and it simply becomes a fluid. No free surface, everything behaves like a vapor, a fluid, above this critical point, okay? All right, I want to finish up one more thing, and then we'll do an example involving this on Monday. I want to point out, I guess I'll do it over here. I want to point out that I could have done the whole experiment I could have done this whole experiment not doing constant pressure, but I could have done constant temperature. I could have done this whole experiment using some kind of isothermal device. I could have put ice. So I could have had my piston cylinder device here. And I could have had H2O. And I could have put, I don't know, I could have put something here that it was at some constant temperature. I could have put the H2O into contact with something at some constant temperature. T equals a constant. And I could have done the whole experiment that we just did a few minutes ago, adding heat and boiling stuff and vaporizing H2O. I could have done that at constant temperature too. And that would have produced a pressure volume diagram. Pressure specific volume. Okay? And I would have had a dome. I'd have a dome that was very similar. Same shape. Here's the critical point. Right up there. Along this side of the dome, I have saturated liquid. Over here, I have saturated vapor. On this side of the dome, here I'll have superheated vapor. In other words, a gas. And over here, I'm going to have supercooled liquid. Supercooled liquid, okay? It'll look the same. Now, instead of having an isobar in here, because I got a PV diagram, I'll have an isotherm instead. I'll have an isotherm. And the isotherm is going to be downward instead of upward sloping. It's going to be down on the left, horizontal in the middle, and downward sloping in the superheated vapor region. So this is a T equals constant. Or my isotherm. Isotherm. That's what the isotherm looks like on the PV diagram. Think of it this way. If you have a gas, let's say H2O was a gas held at constant temperature. Let's say you reduce the pressure. It's a gas and you reduce the pressure. Pressure went down. As pressure goes down, volume or specific volume goes up. You lower the pressure on something, a gas, and it expands. As pressure goes down, so I'm moving to the right on the PV, moving to the right and down on the PV curve along this isotherm. As pressure goes down, volume goes up. Pressure goes down, volume goes up. So that's the way I remember that it's a downward sloping isotherm in the PV diagram, okay? All right, ladies and gentlemen, we're gonna do an example with this next time and try to, we'll let this solidify and gel and get you to sleep on this. This is a lot of material. I encourage you to read the relevant section on the phase diagram and the saturation dome, either in the notes or in Moran and Shapiro, because this is kind of, some of you have seen this before. For those that haven't, I suggest you hit it from a different source and get another point of view. So on Monday, we'll do an example involving the saturation dome. And then we'll talk about calculating properties like specific volume, temperatures, and pressures for various phases of air or H2O. We'll start working with these phase diagrams here, okay? Start working with these phase diagrams. All right, ladies and gentlemen, that's it for today. Take care.